The plane was tens of thousands of meters high, with both engines shutting down simultaneously, but it didn't fall from the sky like a rock. In 2001, while Air Canada Ocean Airlines Flight 236 was flying across the Atlantic, a fuel leak caused fuel to continuously drain, and both engines eventually shut down. At this point, the plane was still hundreds of kilometers away from the nearest airport. Yet, incredibly, this passenger plane, weighing hundreds of tons, did not crash into the ocean, but continued gliding forward and ultimately landed successfully. This raises a question: what exactly makes airplanes fly? Many people think the answer is the engine. The stronger the engine, the higher the plane can fly. But if that were the case, the engine would have stopped and the plane should have crashed immediately. However, reality is quite the opposite. Even when a modern airliner loses all power, it can still glide over long distances. What truly holds the plane back is never the engine, but the air. Air is invisible and intangible, but when an airplane approaches 900 kilometers per hour as it shoots into the sky, the originally soft air becomes as hard as a strong wall. Every second an airplane flies, the air flows through its wings, which generates a large amount of air, and lift is generated during this process. Many people have learned this explanation from textbooks. Air flows faster and lower above the wing, while pressure below is higher, creating upward lift. This explanation is not wrong, but it is not complete, because if pressure were the only thing that could be different, many planes that could fly wouldn't be able to fly at all. The real secret lies elsewhere. When the wing moves forward, it continuously deflects the air downward. According to Newton's third law, when air is pushed downward, it also pushes the wings upward. In other words, the plane is actually moving forward by stepping on the air. This is hundreds of tons of steel supported by countless invisible air molecules. But the wings themselves do not generate lift out of thin air. When the plane is parked on the tarmac, the wings are not much different from ordinary metal plates. What truly brings the wings back to life is speed. During takeoff, the plane accelerates continuously, and when the speed approaches 300 kilometers per hour, the lift generated by the wings finally exceeds the aircraft's weight, the tires leave the runway, and the plane officially returns to the sky. To help the aircraft fly more efficiently, engineers also designed many details, such as the wings used for takeoff and landing, and the upward raised winglets at the wingtips. They can increase lift, reduce drag, thereby lowering fuel consumption and improving efficiency. And what keeps the plane moving forward is the engine. Many people think jet engines are like giant flamethrowers, but in fact, taking mainstream high-bypass turbofan engines as an example, most of the air never enters the combustion chamber. The huge fan at the front draws in a large amount of air every second, then pushes this air backward at high speed, giving the plane forward thrust. What the engine actually drives is actually air. The faster the plane flies and the greater its lift. Strangely, most passenger planes do not fly close to the ground, but instead choose to cruise at around 10,000 meters altitude. The reason is simple. The air at high altitude is thinner, drag is greatly reduced, and the same amount of fuel can fly farther, faster, and more economically. So, from the airline's perspective, high altitude is the most cost-effective place. But high altitude also hides dangers. Once the air thins, the aircraft must maintain sufficient speed. If speed continues to decrease, airflow cannot flow smoothly over the wing surface, and lift will rapidly weaken. This phenomenon is called stalling. For pilots, stalling is far more dangerous than engine shutdown. And the most surprising move happened right here. Many people's first reaction is to pull up the nose, but doing so only further slows down the speed. The correct approach is actually to lower the nose and accelerate the plane's dive. Once the speed is restored, the airflow reattaches to the wing surface, lift reappears, and the aircraft can resume normal flight. In other words, when the plane starts to fall, the pilot must first make it fall faster. This sounds completely counterintuitive, yet it is one of the most important aspects of aviation training. However, today's passenger planes have become increasingly smart, and many traditional mechanical control systems on the new generation of large aircraft have been replaced by fly-by-wire systems. When the pilot pushes the control stick, the command is not directly transmitted to the control surface, but first enters the computer, which then determines safety before controlling the aircraft to perform the action. Even if the pilot suddenly makes a dangerous maneuver, the computer may refuse to execute it. In a sense, modern passenger planes are no longer just airplanes, but supercomputers capable of flying. Many passengers are also afraid of turbulence. Whenever the plane bounces violently, some worry that the wings might break. In fact, modern airliner wings are much stronger than imagined. During testing, the wings can even bend significantly without breaking. Most turbulence only cause discomfort when riding and do not threaten the safety of the aircraft's structure. And landing is also a matter of precise control. The plane was traveling at nearly 300 kilometers per hour, nearing the runway. The moment the tires touched the ground, the spoiler quickly rose, actively disrupting lift and firmly pinning the plane to the ground. At the same time, the engine activates the thrust reverser system to help the aircraft slow down. The entire process seems simple, but behind it lies the collaborative effort of countless engineering technologies. Now, returning to the original plane, Ocean Airlines Flight 236 still glided over 100 kilometers after losing all power and ultimately landed successfully, with all 306 people on board surviving. This case proves something many people don't know. Losing an engine does not mean losing flight, because what truly keeps an aircraft in the sky is never the engine, but the continuous interaction between the wing and the air. Today, humanity is still developing the next generation of aircraft that are quieter and more environmentally friendly. Technology is constantly evolving, materials are constantly upgrading, and computers become ever more powerful. But one thing has never changed. When you sit in a cabin 10,000 meters above and look out the window, there are no roads, no bridges, no supports beneath your feet, only invisible air. It is precisely this invisible air that lifts hundreds of tons of steel and also carries humanity's dream of soaring into the sky.